now we're going to look at testing a hypothesis test with two independent population proportions. And so when I do this, there are some characteristics that have to be present. I have to have two independent samples that are simple random samples. I have to have a number of successes of at least 5 and a number of failures that's going to be at least 5 for each of my samples. And there's a growing group of literature that's looking at this level of 5 and making some other suggestions. We're going to keep the population from being oversampled, which would cause some bias and incorrect results. When I'm comparing the two populations, it's similar to two proportions. It's similar to the two means, like we just learned. If the two estimated proportions are different, like if I had two different means, it could be due to a difference in the population themselves or just due to chance. So a hypothesis test is going to help us determine if there's really a difference in those proportions, but it's not going to help us always make this concrete, yes, this is related, because there is always that possibility that it's happening with chance. So to conduct this type of test, we use what we call a pooled proportion, which is going to be P of C. And I'm going to take those X values and add them together, and I'm going to take the N values and add those together, and that's how I'm going to come up with this pooled proportion value. The distribution for the differences in my proportions is going to be this giant formula, and then my test statistic. Again, you can use technology for these. You do not have to hand crunch this. So let's look at an example. If I'm trying medication and I'm taking them for hives, so some kind of allergic reaction, and I'm testing it to figure out if there's a difference in the proportion of patient reactions, not the mean, the proportion, 20 out of a random sample of 200 were given medication A and still had hives. 12 out of 200 and given medication B, so I have two distinct groups, still had hives. So if I want to test this at a 1% level of significance, that's a pretty tight test. So I'm going to look at the different things here. I'm going to set up my hypothesis. It's very similar to what I did before. The difference of proportions who did not react after 30 minutes, we expect them to be the same. So that's my null hypothesis, that they're the same. My alternate hypothesis is that they're not the same. So this is very similar to what we did with the mean test. So the words difference tell you the test is two-tailed because a difference implies subtraction. So for the distribution, I'm going to calculate my value. And it's two binomial population proportions because I had those successes out of total. And my distribution is going to be normal. So I'm going to complete the calculations using the formulas that we did. Once I complete those calculations, I'm going to start placing things into the distribution image. So I have a p-value using the normal distribution of 0.1404. My critical value is found from subtracting the actual proportions. So to find those actual proportions, I'm going to have 20 over 200, 12 over 200 from the information in the problem. So when I subtract 0.1 and 0.06, I get 0.04. There's my critical values. With half the p-value below 0.04 and half above 0.04, I'm going to use that information to compare my alpha and my p-value. Since it's 1%, I have alpha is 0.01, and the p-value that I calculated is 0.14, so my alpha is less than my p-value, so my decision is I can't reject the null hypothesis. So here's the thing, guys. The population proportion, what we're really doing here is we're executing a test very similar to the two means, but the calculations that are being done are different. So the way that I get my p-value is different, but the process is the same. The rules are the same. The rules don't change. So this should help you get those two population proportions and complete that hypothesis test.